It's time for our second panel of the day. This is going to be integrating emerging technologies. And again, going from right to left, we have Diego Dominic from Power Electronics, Daniel Tabus from Base Power, Derek Haas from the University of Texas, Alex Shattuck from the Energy Systems Integration Group, ESIG, and Texas Re's Mark Henry, who is our Chief Engineer and Director of Reliability Outreach, will be the panel moderator. Mark, take it away.
All right. Well, again, welcome. I'm looking forward. We're going to pick up. In the previous panel, we talked about load and load growth and a whole bunch of other related issues. There's a lot of questions there. In this panel, we're going to be talking more about resources that we need to produce energy, sometimes in different ways, or provide energy. Even if some of the large load expectations are overblown, we know in ERCOT we have an aging fleet. There is growth beyond what comes with the more exotic data centers and things like that. And so we're going to be talking about the changes that we see happening and the ability to supply energy for our loads. And we're going to start out in an area that was touched on by Jim Robb and also in the last panel, and that's about ERCOT and the ERCOT market construct. And what we want to explore here a little bit is our construct here supportive of the technology evolution that's been going on and that we can see in the future, and is that going to also support operational reliability? And Daniel, we're going to let you start that out because you have one of the more prominent companies associated with bringing in resources with Base Power.
Mm-hmm. Yeah, so in terms of whether ERCOT and the market construct really supports the development of new technologies, it's kind of a yes and no type of thing. On the one hand, ERCOT doesn't have a capacity market, and anytime you're developing a new technology, you're placing a bet. And having a capacity market is one way to ensure that that bet is going to be de-risked a little bit and that it's going to pay off. So not having that could, in theory, make it more difficult to take some of these technological risks. But on the other hand, having a capacity market can actually make it difficult to deploy new technologies. So for example, at Base Power, we're developing the first distributed energy resource that is purpose-built for grid support. So our batteries are developed as grid assets as well as providing home backup. And integrating our distributed resource and actually using it to provide grid support at the aggregated level is something that would be very difficult if we had a capacity market in place. It would take multiple years and many steps and lots of certification in order to actually get our resource certified to participate in these capacity auctions. And so there's really nowhere else in the country where we would be able to do what we're doing, which is deploying thousands of batteries, integrating them, and participating in ERCOT's aggregated distributed energy resource pilot program. So that's something that, that's an example of something that we're able to do here that we couldn't do other places.
And Dan, that's just fits right in line with a lot of times we characterize ERCOT as the national lab.
Yep.
Alex, you got anything to add to that?
I do, and since Dan gave a market answer, and I'm not a markets person, I'm going to choose to interpret market as ERCOT as an area.
Okay.
And I'm going to include the regulatory structure in that as
Fair
well.
enough.
So in that sense, yes, certainly. ERCOT is set up to promote and integrate these new technologies, and there's a number of reasons for that. One, you're a small island, and electrically, and that allows for some rapid change in regulatory structure. If you look at what NOGRT 245 has done in such a short time, even though it's been an argument and it's been hard and fought and that type of thing, it's been a massive step change in performance requirements, interconnection requirements, reliability requirements that are accelerating and adapting much quicker than, say, NERC or FERC. And there's obviously reasons for that, right? There's a lot less, as you go down to the local level, there's a lot less upwards red tape that you see from, really slow-moving FERC directive processes or, multiple-year NERC standards processes. And ERCOT's been able to do that through much more rapid regulatory change, right? And that's pretty much, in my opinion, the key to integrating new technologies is to have a regulatory structure to let them come and do it reliably, right? To have performance requirements so that people who are coming know what they can put in their system or in their products to come to ERCOT. Having interconnection requirements that are clear and detailed also helps the integration of these technologies, because in the rest of the country, and if there's still some in ERCOT, most of it's confusion, right? If I want to do something in ERCOT or do something in New York, I need two separate legal teams to understand the different processes and things like that. And the NOGR and the other processes in ERCOT have rapidly but they've accomplished in filling those gaps and giving more certainty to, what do you need to do to even consider joining ERCOT right up front. And it's much easier to say, to join and integrate your new technologies in ERCOT's grid, in my opinion, because there's more certainty, more detailed requirements, a lot less judgment, which can really delay lots of things. And all those things together, I think, makes ERCOT the test lab for new things.
Sure. Again, it opens things up. And sometimes maybe we get a little ahead of ourselves, but that's life. And behind all this stuff in the ERCOT market, I was around when the changes were made at the turn of the century. And it was the legislature that was behind that. And in the previous panel, in this panel too, we're going to talk a little bit about what's the role of government. Our Texas legislature just passed some bills. We talked about Senate Bill 6. There were a few bills that affected other parts of the industry. And then we've had federal rules. One big, beautiful bill. It seemed like that's had some changes. And just want maybe y'all to give us some thoughts. And Derek, you can start out. What do you think is the right role for government? And there's I guess a long and a short term aspect of that too. But what are your thoughts about how government needs to be engaged with our industry?
Well, that's a dangerous question, Professor. My focus is nuclear energy, and so I'll talk a bit about that. At the state level, a year and a half ago, the governor stood up a committee to look at how nuclear can be expanded in Texas. We worked on that for just about a year, put together a report that was released. Those recommendations worked into the last legislative session, and we have a few bills that came out. The highest priority one was HB 14, and that put together $350 million in incentives for building and bringing online new reactors in the state of Texas. The $350 million was certainly less than what was hoped for at the beginning from the industry. I think that on the promising side, what has come out was this looks like an initial investment from the state of Texas to look at nuclear energy. So it's a first step. The hope is that it spurs projects to move forward in the state. We have a few going on at the moment, and there could be more starting any day now. And so that bill and that it's pushing forward a bit and trying to bring some of that industry to Texas. I think one of the areas that's hard to get too much buy-in at the moment is nuclear especially is going to take a while to start impacting the grid. It just takes a while to come online. You have to put a lot of years and a lot of commitment and a lot of money up front. Once you start doing that, you can bring a lot of generation online in big chunks. So hundreds of megawatts to gigawatts over and over and over again very rapidly. And so that'll be part of that problem. The other is we could grow a lot of that industry here that we then export the reactor technology to the rest of the world. And so there's an industrial component as well. It's more complicated than just how do we put new generation online as fast as possible.
Yeah, and I know nuclear can also provide other things just besides electricity. We're starting to hear about projects in that space. So, but it certainly is something that's going to take time, and I guess the government has a role in getting things started. But Diego, let's talk about some of the things maybe the government's done that impact things that are already rolling a little bit.
Yeah, so I think there's plenty examples in ERCOT where we can see they're actively promoting or improving the grid resilience and reliability. Some examples of this are the nodal operation guides, which are the NOGR 245, NOGR 255, and NOGR 272. The NOGR 245 is just a guide, obviously, with a set of protections at inverter-based resources, at the end, it just fixes voltage and frequency protections thresholds, either up or higher of their nominal value or lower than the nominal value for a given time. And they say you must need to remain connected for this amount of time. And this sort of protections are common in all of the world. These profiles are given in each one of the grid codes. But it has a quite pioneer or new way of thinking, specifying that I give you this set of protections, this set of profile or protections of frequencies and voltage, but you need to maximize these protections according to your capabilities. And it might seem trivial, it might seem obvious, but this is an approach that no other grid code that I've known has. In this sense, it makes the inverters manufacturers to remain connected and remain resilient into grid events. And that's a really important approach because it's not a matter of limiting your protections to a fixed profile, but trying to get the most of each one of the inverter-based resources and avoid any sort of disconnection that might lead to the future blackouts as a consequence of a grid event, both in voltage or in frequency. There's several more examples, such as NOGUR 255, which I also think it addresses a clear factor that it's really important in terms of grid resilience, and it's monitoring. And again, it might sound trivial, but it really not. When you have a mix of generation and that is continuously evolving, you need to be ready to monitor every sort of grid event, analyze it, and see what are both the consequences of integrating this sort of energetic mix, and see how we address each one of the type of new events that may come. And finally, NOGUR 272, which is for grid-forming inverters. This is also a quite pioneer standard. We see that mostly the countries that have a high penetration of renewable resources tend to start talking about grid forming as a possible solution to IBR, high IBR and renewable integration. And a good thing, or a thing that I particularly like about NOGUR 272, is that they are able to look back to countries which currently have grid-forming inverters in operation, such as Australia and AEMO, and learn about what is being done around the world and taking it to your particular grid with their characteristics. And at national level, and standard that I think is going to be a game changer, or that it's already is, I think it's IEEE 2800, both the 2800 and the 2800-2. I think this provides a clear set of standards that can be integrated all around the US nation, and I think that brings many benefits. I think it's a huge advantage, to be honest here, because you can make design, manufacture, and planning to a common set of standards, either if you partially or totally adopt this standard in each one of the ICOs around the US. That's important. But just going in the same pathway, I believe it will reduce costs on overall projects. I think it will make deployments faster and overall increase grid reliability and grid resilience.
Could I add some to that?
Yes, please do.
I mean, I'll answer the question really directly and say the role of the regulatory apparatus is key. And the reason why I say that is before I joined ESIG, I worked at NERC.
Right.
And I wrote all three of those alerts. The third one just came out. Well, the third, the one that I wrote, the third one I wrote came out, which is the best one. And if you all have trouble sleeping, you can read through them in detail, and there's lots of statistics in there to back up what I'm going to say. But one of the key findings, and I fought really hard to make sure it's in there, is recommendations do not work. Best practices don't work. Voluntary recommendations don't work. So how do you get people to do something? It's a regulatory construct. There's a standard, there's a law, there's a FERC directive. There's something like that to tell you what you need to do to be reliable. Obviously, that can get out of hand, right? If there's not like a firm technical foundation in what is the bare minimum to do something, to keep the grid reliable. But that's also a mindset that is a little bit troublesome for us moving into the future of the grid, which is in the past when it's a large engineering company building a gas turbine or an engineering company building a nuclear facility. There's a lot of regulations that go into that. And those companies typically have engineering leadership, engineering principles, guiding their design and their interaction with the utilities and things like that. And now we're in a situation where, up until recently, there was a lot of tax incentives to install IBR.
Right.
And when there's tax incentives of that level, who are the main players? Investment capital banks, right? There are hundreds, maybe hundreds, but there's hundreds of megawatts of IBRs out there from companies like BlackRock or Capital or Berkshire Hathaway. And I was at an OEM for Vestas, who's wind, and when we were interacting with those companies, they might not even have a technical person on staff.
Yeah.
They may not even employ an engineer. So how do you get there? How do you get reliability as a base there, right? And what their motivation is to get that thing connected as fast as humanly possible, sell megawatts and make money, which is not the same, that motivation does not align with keeping the grid and the lights on, right? So we have to have a regulatory technical minimum. The technical minimum right now is not sufficient. You can look at the 25,000 megawatts of NERC disturbance reports that have shown that none of the planning processes predicted any of these. Interconnection, long-term planning, resource adequacy, none of those planning processes predicted any of those 25,000 megawatts. And that's not all of the megawatts either, right? Those are only the events that were big enough to categorize a mandatory report. There are gigawatts and gigawatts of unexpected reductions that don't even make it to the NERC major report reporting, right? So there's a huge gap. And the way to fill that gap is to make it mandatory, and it is the technical minimum. The technical minimum has to be set by, engineering consensus, and I'll make a plug for 2800 and 2800.2 by IEEE standards. One's the recommended best practice, and I was drafting the base standard, and I'm leading subgroup 3, which is design evaluation and model verification for .2. So really entrenched in these and those types of kind of international technical consensus in a voluntary standard where you get more of a pure technical outcome.
Right.
Those could be leveraged to new regulatory pieces in the U.S. And that plus looking at our neighbors across the sea, right? Europe, particularly Germany or Ireland or Australia.
And Spain.
Yeah,
Yeah.
we'll get there later. Yeah,
We'll get into that.
we are as the U.S. are behind as far as penetrations are concerned. So we can learn a lot from our neighbors. We haven't had much palatability to do so for whatever reason, but we should, and that would really make it a lot easier for us to learn and get good technical founded minimums, and the rest of it kind of fills in.
Yeah.
And if I can add,
Please.
I really learned a lot from Jim Robb's keynote this morning, and I'm over here taking pictures because his first slide that had all that information about all these risks that are coming at us and all these potential ways that we can solve them, I'm going, nuclear can solve almost all of those. The problem is it is one of the most expensive as far as the next piece on the grid. But if you look at all these other things that we're going to try to spend money in other ways to try to solve those, what we can do is incorporate that into the next generation that gets added, like nuclear power, that has a lot of those things already built in, like the security. Nuclear plants are very secure, and so we've already built that in. It's already part of the cost. Most of those other bullet points on there are things that nuclear can provide, and so how we figure out how to properly value those things is going to be really important going forward.
Absolutely. And one other aspect that I wanted to touch on again with the federal bill that passes apparently are subsidy practices for wind and solar, and I guess to some degree other things are changing. The industry has been able to benefit from that, I believe, and has certainly brought costs down such that when I started in the business, wind and solar was a dream, and now it's everywhere. Are we seeing the government action there coming at a time when the industry hopefully can stand on its own in those areas? And this affects other things too. I'm sure there are other aspects of policy change that are important. We've focused on developing the regulatory rules that will guide us and operate in the system, but there are the other incentives. And how is that playing out in y'all's view?
Well, I'll start off and just say,
Okay,
when,
sure.
when you're talking about nuclear, because it is so capital intensive and takes many years to get deployed, so 5 to 8 years to deploy, you need consistency. And so I think as we move forward, consistency is really going to be the most important thing. Obviously, incentives are great to help spur those first investments. I do think when you talk Texas, probably the first adopters of nuclear are going to be industrial, either behind the meter or pre-purchased PPAs with agreements there. And so, yeah, I think the more consistency we can have, the better. I think improvements in licensing and permitting are already happening, and they're just being further accentuated in the current executive orders and the big, beautiful bill. I think that I used to think permitting of nuclear reactors was going to be the major hurdle. The experience I've had working in this in the last few years has shown me that that's getting a lot better very fast. And now the question is going to be, can we have the consistency in incentives, but also in those financing to get the things off the ground? And so consistency.
Yeah, I mean,
I can echo some of those
Please.
points. We're working for a company that is a big energy storage developer. Consistency is definitely key. So we've had to pivot several times recently in terms of like financing and supply chains and stuff like that. And so it's important to be able to know like where you're going to procure your materials and cells and things like that for assembling batteries. And it's also important to have a good long-term view of how those projects are going to be financed. And so, like, yeah, ultimately, the slower things change, the better.
Yeah, and if the incentives were to go away, I think now is okay. In my personal opinion, like I think we're at a point where the cost competitiveness is becoming less of a concern, in my opinion. And the other aspect of that is not related to policy, but if we're going to win the AI race, right, and meet all of this demand, where's the megawatts going to come from, right? Has anyone ever, what are the lead times for a natural gas turbine right now? You're not getting a new one until 2031 or something like that, right? So where's it going to come from? Even if it's not cost competitive, we want to have these other goals like data centers on large loads and things like that. They're going to get, if you want the megawatts, you're going to have to build something. And the available technologies right now, even with the supply chain constraints, are IPRs.
Yeah, that's right.
So even without the incentives, there are other incentives that maybe aren't monetary, but functionally, right? Specifically meeting the growing demand with, you're not going to do it with just gas. You're probably not going to do it with coal either, and you're not building a nuclear till 2035. So
2030.
okay. So where's it coming from? So I think it's okay. That's a lot of lifting the word does, but it's okay for now, I guess.
Yeah, that's the situation we find ourselves in, and capabilities out there, but how the government is involved with that, and how our markets are involved with rolling things out. I want to shift gears a little bit and go back to some of the things Diego was bringing up about grid codes and improvements and things of that nature, and cutting closer to your birthplace is we're starting to learn some more about the Spanish blackout. And certainly here, as Alex was pointing out, we've had a series of disturbances where IBRs were not able to ride through. We've done a lot of work since then, and I just kind of wanted your thoughts about, we don't know everything about the Spanish blackout. It looked to me like there were a lot of operational miscoordinations and decisions about the relative role of resources. and not so much about the inability of these resources to be integrated. We just weren't using them as effectively as we could be, and we weren't remembering interactions. What thoughts do you have about that and where we stand? I'll say in ERCOT primarily, but again, you're familiar with grid codes around the world and events there.
So, starting with, I think that the Iberian blackout was a warning call for any advanced grid with high penetration of renewables, and it obviously brings question of like, why did this happen, or how can we solve it, or is it my own grid, in this case, ERCOT, addressing this high penetration of renewables effectively to avoid this sort of events like blackouts. So I think it's worth stepping back to the actual blackout and seeing what actually happened. There has been plenty of reports, discussions, analysis, and to be honest, I don't think it's 100% clear the exact root cause that caused the blackout. In my opinion, I think there was several factors. I don't think we can attribute this to one single reason. I think there's several factors and probably mistakes that occurred that made this blackout happen, right? So if we go exactly to the blackout, we can see that there was in the southwest of Spain some renewable generation disconnection that essentially brought the frequency down to its under the nominal value, and that caused that other generation plant automatically disconnected due to frequency protection, including the French interconnection in the north. So many people at first addressed this to renewables, like these are the problems, and I don't really think it's a fair statement. The grid operator must be ready to ensure there is a fast, reliable generation backup when you lose some generation, because these things can happen. Power plants can trip, not only renewables, but any sort of power plants can trip for several reasons. So there must be sufficient backup, as I said, with resilient and really fast response, such as energy storage system, BESS plants. That is the first one of the first important keys here. There is not really a great amount of energy storage system in Spain, and also it doesn't seem there was adequate planning to ensure that there was a fast response to a loss of generation. And this is even more concerning by the fact that geographically Spain is a peninsula that is on the southwest of Europe. So just geographically, you're limited with your interconnections with Europe. You just have an interconnection in France, and also in the south with Morocco. But sticking with Europe, it's not the same losing power generation when you're right in the middle of the European continent, and all the neighboring countries are just pumping or injecting active power into the system to bring the frequency up. So that's a really important factor that you must consider when you are planning. You need some fast backup in the system, and going even to the start of the blackout, we see some voltage regulation, voltage disturbances that weren't addressed properly. They weren't properly damped. So we can see if this is an issue of damping, of regulations that must be updated to have a more stringent grid codes, more aggressive voltage regulation with a high penetration of renewables, and also with the renewable generation disconnection that happened due to these voltage fluctuations. It would be interesting to see if in planning, during commissioning, all of these protections were rigorously tested and ensure that they were inside of parameters. And if we just look now at ERCOT with this with this information. So I think that ERCOT is approaching the high penetration of renewables in an effective way. Also, since the Odisha events in 2021 and 2022, we see key factors to address this sort of high penetration, because there are similarities between Spain and the Texas state. We see a high penetration of renewables, PV and wind mainly. We see Texas, which does not characterize by having really large amount of interconnection. So nowadays we need to support and provide enough energy storage system and other technologies for sure, but this is where my expertise is. So energy storage system could be really important, and even more with grid forming capabilities that can provide synthetic inertia, really fast responses in terms of frequency. For example, fast frequency response here in ERCOT is one of the fastest in the world, alongside Ireland and Australia. 250 milliseconds to deploy up to your maximum potential of your power plant is a really fast deployment that can actually help to mitigate this frequency drop due to the loss of generation. So energy storage systems, we have seen in ERCOT that there has been a really high amount of these energy storage systems BESS plants commissioned in the last 2-3 years. We have seen around 10 gigawatts or even higher of this. And as we were talking before, at the beginning of the event, this is the NOGR 245, NOGR 255, and NOGR 272 directly avoids this sort of things to happen. For example, maximizing protections. We were seeing that really in Spain, once the first generation was stripped and we didn't have enough power or fast enough power to sustain the grid, we saw that many generation plants tripped, and maybe maximizing these resources would give us seconds, minutes, even hours to try to restore the frequency as fast as we can. So I do really think that ERCOT is currently approaching in the last 2 or 3 years or addressing this high penetration of renewables effectively. And if we look back to the blackout in Spain, we can see many similarities and also standards, regulations, and market moving towards a resilient grid here in ERCOT.
Yeah, we know it's an adjustment for the owners who've installed equipment already to come back and make some of those changes. Do y'all have any other thoughts about that, Alex, in particular?
Sure. I'll pick one piece of the Iberian blackout and then add one little bit of speculation, then go about what I'm going to say. So one of the main things, in my opinion, of the voltage regulation piece specifically is that a lot of the IBRs were in power factor mode.
Right.
Which, for those who don't do control, power factor mode means you're given a power factor, which is a set Q for your nameplate, and you just sit there and you just do that forever. That's not really a problem in ERCOT.
Right.
And in a lot of the U.S., most areas have a automatic voltage regulation requirement. ERCOT specifically has performance requirements that say if the voltage is high, maximize inductive. If the voltage is low, maximize capacitive. So that's good in ERCOT specifically. For the rest of the country, and there's a really big problem, and this is something I've tried to get through publishing a number of times, but FERC Order 827 is miswritten, just plain out miswritten. So 827 is a FERC order that says you must provide reactive power control. But they say, the order says within 0.95 and positive 0.95 power factor, which means you're never giving more than your power factor. You're in this tight little window around your nominal power factor, right? Which I think I may have got that in that second alert report. If you check the alert report at the end of it, there should be a graph that shows what's left off the table at a typical plant.
Yeah, that's that alligator graph,
Yes,
I like to call it.
Yeah, there's a massive red shaded area of reactive power you're not using that's sitting there. because FERC Order 827 says so when it shouldn't. So I think there's filings to fix that, but that gives us the same situation or similar situation of a potential to not have enough reactive power to keep the voltage up or down during disturbances. And just really quickly, overarching kind of mindset in the US specifically is, and I think, I don't know, speculating wise, how this went into Spain, but if I was operating in Spain and I put everything in power factor mode, I think that kind of lends itself to the US mindset of, which has been for a long time, is put the IBR in and we'll plan around it. Put it in, tell it to do something we expect, maybe put it in power factor mode, put it in a droop with 3% or whatever, and we'll design around it. It doesn't work with high penetrations anymore. Even 6 years ago when I was doing planning studies, we turned all the wind off for the summer peak. We just said, we're not going to count on it. It's never going to be here. We don't care. Turn the wind off for summer peak. Solar was at 10%. So we didn't even treat it as a resource, even just 6 years ago or 8 years ago. So that mindset needs to change. We need to be able to fully utilize all of the IBR capabilities that we just aren't. We're leaving a lot of advanced controls on the table that are going to be necessary for weak grids or advanced voltage support or fast frequency response or artificial inertia. All these things are out there. They're in the code of these IBRs, but no one turns them on because either they're not incentivized or no one asked them to or no one knows they exist.
Yes.
But they're there. So.
And you kind of touch on, and I want to get into the next question. And Mr. Rob brought that up this morning, or one of the questions was about our workforce. And I'll lump that into the broader topic of the supply chain, to get the things manufactured, to know what to do with the things. My impression is that the IBRs are quite flexible, capable, but you have to spend the time to understand the capability as part of a vendor for inverters. You definitely know that firsthand. We've seen that in other things in my time in the industry as digital technology is extremely capable and flexible, shows up. You have to spend the time to understand the difference. Derek, do you want to start that one off about, I'll say supply chain in general, but I want to make sure we talk about the people, because in our event analysis and things that are going on, we see that as a concern, being able to get the answers and folks who have spent the time up front to understand, as well as getting the equipment in the first place.
Absolutely. So in nuclear specific, it's a really interesting supply chain problem. Because of the energy density of nuclear, the total number of tons of material is not that high. It's the fact that it's a specialized supply chain that requires a specific higher level of QA in order to sell that pump or that electronic system or those kinds of things. The bad thing about that is it takes quite a lift to get over that threshold to be able to sell those nuclear qualified components. The good thing is once you do, scaling up is not that difficult because the total number of tons of material is not that high. So getting over that threshold is going to be the next challenge for nuclear energy. After that, I fully expect it to be one of those areas that disappears from the primary focus of deploying more nuclear. I think the longer term thing will absolutely be the workforce. So I've participated in a lot of events like this one in the last couple of years as folks remembered that nuclear existed. And so not only are we looking at scaling up, we're also, we've got an industry that's been around for 60 years. Most of the people that developed and still operate that industry are about ready to retire, or they've already done it. And so we have a compounding issue of the existing fleet is having to recruit like crazy. A lot of the same people that we hire into nuclear energy are also being sought after for nuclear nonproliferation and international security. So I get representatives from US national laboratories that come in and say, I'd like to hire all of your graduates. And I say, you and every other laboratory and quite a bit of industry. And then we talk about workforce at meetings like this, and people flag it and say it's really important, but there isn't a lot of follow through. And so figuring out how to do that is going to be crucial. We sent out, my group sent out a survey to about 60 industry and academic representatives last week. We're looking for input, so if anybody would like that, I'll plug that and say, my information's on the website. I'm happy to send that survey out. We're trying to collect the systems that are already out there. There's quite a bit of small focused workforce development programs in individual companies at very localized community colleges, serving just a couple of nuclear reactors. Trying to build that into a statewide, national or international workforce development program is going to be complicated, but we don't want to start from scratch. There are good systems already being used and educating folks today. We just need to figure out the best ways to scale that up. So it needs to be more than a checkbox talking point. Yes, we need workforce development. It has to be a specific concerted effort to try to bring these things together. And the promising thing is the student interest is already there. About 5 years ago, we were having trouble getting enough students to register for nuclear engineering classes so that the registrar wouldn't cancel the class. Now we're having to move the classes to larger classrooms because we're overbooked. So the student interest is there. I get emails every single week from incoming students or others that want to get involved, and that includes both engineering majors, but also economics majors and business majors and policy majors, all wanting to learn more about this. The other thing is we need to scale that not just for the traditional bachelor's, master's, PhD degrees. For every one of those, we're going to need 9 or 10 skilled craft
Trades.
folks, and we don't spend much time on that at all. That's got to be a new focus area.
Yeah. Dan, I'm wondering, in your business, you are going to rely a lot on trades folks to go up because you've got a lot of equipment at residences and I guess businesses. How is that playing out in your company's development right now?
Yeah, absolutely. So if you know anyone in Dallas, Fort Worth, San Antonio, Houston, Austin, yeah, we are hiring electricians all the time. We have multiple teams going out every day, installing batteries at people's homes, doing field service on the battery modules and the inverters and the hubs. And yeah, we really rely on them for our business model. And we have grown our team a lot, but it is at the same time difficult to find people sometimes. So yeah, we definitely need a larger workforce of skilled electricians.
Yeah, I see so many things that take skills and knowledge that I won't say that we didn't need it before, but it's so diverse. The things that I had to learn about how synchronous machines work and how electromechanical relays were set up, well, they're still out there, but now we've got to add all these other things with it as well. Certainly some things may help us, and I kind of wanted to touch on that. A lot of what we talked about in the first panel was about data centers, and behind that is artificial intelligence. And what I wanted to ask you all is how do you see artificial intelligence perhaps increasing our ability to integrate these technologies, develop new ones, and to supplement the workforce that we have? I wanted to take that one maybe to finish with it, and then we'll see what questions that we have coming in from the listeners.
Yeah, so I think artificial intelligence has a lot of roles to play, but also it's a concept that's difficult to define.
Yeah.
So if you go back to like the 60s and 70s, what they were doing with, or what they were calling AI was like a computer program that would solve checkers. And they would do so by like having a bunch of hard-coded decision rules. If the board looks like this, then you do this. Or if the board looks like that, then you do that. And that was AI. And it's evolved a lot since then. I think over the past like year or two, there's been a lot of hype around these large language models, but I don't think that those are the secret sauce that's really going to get us to operating a flexible grid. What we really need is intelligent algorithms for forecasting and decision and control. And so at BASE, we're developing some algorithms on all those fronts that take into account the unpredictability of electricity prices and ancillary service prices, as well as the load and solar production that's occurring at each of the sites where our batteries are installed. And so yeah, there's a lot of kind of intelligence that needs to happen. But at the same time, that requires a lot of data and a lot of compute power. And so with all these new data centers getting installed, like we heard about in the last session, that is also introducing some new challenges for operating the grid. there's a lot of differences in how traditional data centers consume energy versus how these data centers for training machine learning models consume energy. It's much more bursty, much more unpredictable, on-off type of behavior. So yeah, definitely a lot of challenges and a lot of opportunities.
Yeah, I agree. It's not the secret, but it could help. But I'd also preach a lot of caution along with it. And I'm going to lump AI and automation into the same to link it to a real example that happens almost every day, right, in the industry right now. And honestly, it kind of feeds into the education knowledge issue that's happening in the workforce, both in the US and internationally. So really briefly on the last one, yes, the workforce is not where it needs to be in the US or anywhere. And that is knowledge or people to do it. I have a leadership role in a global power system transformation consortium. We have the same problems in Europe that we have as far as workforce in the US. It's not a, US people are dumb, all the smart people are in Europe situation. It's the grid is evolving so fast and so much new stuff needs to happen. There aren't enough people to have practical knowledge. So like AI and automation can help that. I can automate something to run the entirety of ERCOT's interconnection process, right? But what does that help? If I have a new engineer and they're trained by saying, here's our script to do this thing, you just press the button and then the answer comes out and then that's the answer, right? There's no engineering judgment anymore. And that very quickly, 6 months into your job and all you've done is press the button on the script for 8 hours a day, you've forgotten what you learned in college, right?
Unless you used AI on your homework in college.
Yeah,
So.
then you really, yeah. So it's a double-edged sword, right? The tool is only as good as the user, in my opinion. Like, there needs to be a foundation of engineering judgment to go along with that use of automation. And that's a problem that is just rampant, right? I've heard it from directly comments from the NERC process. We don't have the people to do the studies that are necessary. ESIG is, I'm going to plug shamelessly, sorry, real quick. Right. ESIG is doing, or I'm leading if you want to hear me speak more. Maybe you don't. We're doing 2 short courses this year. One of them is on interconnection studies. So practical knowledge, how is the grid transforming? What does that mean for system strength? How do you model an IBR? How do you do new special studies? How do you manage customers who don't have technical staff? Like the real practical stuff intended to be, here's how you build a real world working engineering judgment. Following on that is electromagnetic transient, which is kind of the new up and coming, I hate saying that because it's been around for a while, but more visible, I'd say, EMT simulation solutions for more advanced things like IBR control, fast transients. Grid forming basically is necessary for grid forming EMT studies to do those types of things. So the workforce at current is struggling. The needs of the grid are increasing rapidly, and the gap's going to get wider unless we intelligently use automation tools with judgment to kind of fill those gaps. But a lot of that starts with kind of reintroducing engineering judgment into the workforce, right? Because in power systems, you learn synchronous machines mostly. You learn some signals, some systems, some software coding. An IBR is just a bunch of megawatts behind an inverter who is software based.
Right.
So a lot of the fundamentals don't have a direct translation. So you need that real world engineering judgment to really do your job in the industry now, and that's lacking.
Yeah, we are likely to need to mix the inverter-based technologies and the synchronous machines for a long time because they do have different strengths. And it just creates a very unusual challenge. I remember when the telephone system went from analog to digital, and it created a lot of opportunities. But that's the sort of world that I think that we're in. And looking forward the next 10 years or so, I believe we'll start to see the nuclear facilities being ready and being deployed, and probably for different things than we can imagine, because we've had so much success with inverter-based resources, wind and solar, and we can get them out quickly. And again, it's a way to do what we need. I think that's going to continue, and certainly behind all that, synchronous machines that burn natural gas certainly going to be with us for some time, and who knows what else they may be burning as well. And hopefully we'll have ways to control the emissions that are above and beyond. Thad, do we have any questions? Because I think I'd like to try and cover a few of those things with the time we have left, if folks have brought those up. Okay. All right, we've got a fairly detailed one here. Diego or Alex, this one looks like it's going to be something you can cover. IEEE 1547 was for our distributed inverter systems. That's a set of standards that apply most to manufacturing. And then we've got a docket with our utility commission, which again, if we're not aware of the details, this is something can be followed up on outside. I personally am not too up to date on those things. Anybody have a?
Yeah, I mean, I'm on 2800. I'm
yes.
tangential to 1547.
Yeah.
But just really briefly, I'd say, without getting to the specifics of the requirements, giving requirements for the interconnection process for DERs
Right.
is key. Because then you're telling people what they need to do to be ready to interconnect, to start the process, to give them a minimum for reliability. And those types of requirements and processes are pretty essential for making them reliable. So that's
Yeah.
a vague answer, but.
Yeah, I know that our distribution connection standards lagged. They were made mostly for a time when we didn't have too many of them. We're more concerned about safety. And so this is, again, part of the push because it's understanding now, just looking at the solar rooftop in the ERCOT region, we have probably as much of that in nameplate anyway as we do in nuclear generation, or close to it. And there's more coming. So those are things that certainly have to be factored in, and bringing in the distribution equipment into the bulk grid that we work with mostly in Texas RE and NERC is certainly another aspect of the challenge. Any other thoughts on this one?
Yeah, just one more small thought, sorry. And that's just, again, on the technical requirements. Every second you don't have a technical requirement costs extra money, right? And that's either retroactivity or not leveraging as much of the you could get out of a certain resource with those requirements. So like there's an opportunity cost that is literally ticking every single second. And that goes the same for IBR standards as well.
Well, it's a good question. We may not have got to the heart of it. Diego, you
Yeah,
add a little
I just
bit?
wanted to say that the standards at national level, that adopted at national level, as I was saying before, are really important. Like IEEE 1547, that was the basic standard in which inverters were designed up till now. Now we have new set of standards too that contribute to this development of inverter-based resources. But I think it's also really important to consider standards at ISO or at state level, because you need to understand what's your current generation mix, what issues are you facing in your own ISOs, and how to particularly address it. So I think it's equally important the standards at state level, at national level, sorry, and at state level.
Very good. Thad, another one? Derek, I think this one may fit into yours.
So this is related to the time response of nuclear, which I am absolutely not an expert at, but I'll take a stab at it anyway. But in general, nuclear is not going to be quick response like some of these other things, the digital things we've talked about. It will provide that background stability, spinning reserves, and then the other opportunity for nuclear is to provide, let's say, a long-term, slow-acting adjustment. The key there is that because nuclear reactors are so expensive up front, as your fuel cost is vanishingly small, your upfront cost is high, you want to run it all the time, as much as you can all the time, and so we need to find alternatives. One of the things that has come up a lot is, for any generation technology, is, well, when we're not using it, we'll just do things like make hydrogen or capture carbon or something like that. And then you go and talk to the hydrogen and the carbon capture folks, and they say, if we're going to build $1 billion facility, we're going to run it all the time.
Yeah.
Don't make me turn it off or turn it on. So we need to find other applications that are more, accepting of intermittent uses. And my favorite's desalination. I think that we could be using the heat from nuclear technology to produce water that we're short of in Texas especially, where it's not going to solve this particular question, but I took the advantage and say, we do have other ways that we can add reliability where batteries and other technologies can solve some of these fast issues, but they're not close to solving our long-term storage issues. This is an area that nuclear can help with.
And just to say fast isn't always better, right? I mean, and to your point, the IBR, the best might be quick, but it's not going to be long, right? So you need both, in my opinion, and the handoff is there, right? If it's a grid forming IBR, it's working sub-cycle to fix the immediate response, and then a couple seconds, or less than that, a little while later, the inertia from the nuclear steam turbine picks up, and then for the duration, the base load is there, right? So there's a mix of both, and just because it's a slow, just like the rest of this, steam generated megawatts, doesn't mean it's bad or bad for the grid. It's still going to be a really important piece of reliability.
That's just how we integrate all these things together. Thad, any more questions? Okay. Synchronous condensers on the grid. Do we see that expanding our ability to add more renewable generation? And by that, of course, we're thinking of IBR.
I mean, I'd say yes, for a number of reasons. I'm a grid forming person, but that doesn't mean that all other solutions are not useful, right? If you think of reliability as a ladder, grid forming is a rung, synchronous condensers are a rung. They both get us to the reliability. So this way synchronous condensers help us, in ERCOT specifically for integration of renewables is one, it helps with system strength,
Right.
which we're losing with more retirements of gas turbines and coal turbines and things like that. It also provides a stopgap while more grid forming BESS come. This gives ERCOT a little bit of stability margin until more stable grid forming BESS or maybe PV or others that are coming can come. And that helps both ways, right? One, it's stable while we integrate, and two, it gives some stability margin in ERCOT, because if there's one thing that would really hurt integration of renewables in ERCOT would be a ERCOT-wide blackout caused by renewables. And this type of thing gives us as system people stability margin to get there.
Right. I remember reading one of the papers that you may have had something to do with while you were at NERC that spoke about grid forming. I know Diego had some things earlier about the value of grid forming, but this paper pointed out that you need to have, I'll call it defense in depth. Synchronous condensers provide you capability. The grid forming inverters can add to that. They may have slightly different characteristics. You have any other thoughts on that one?
I mean, I think that the balance here is always doing an analysis of what you have, where you want to go, and based on that, commission and plan the commissioning of different plants and different technologies. As we were speaking before, nuclear is a slower responding technology, but there's anything that's not a bad thing. That's just the way it is. And renewables are intermittent, and that's not a bad thing. That's just the way it is, and it brings several advantages and things you need to regulate. Synchronous condensers are just one more thing you need to add to these equations, and consider the advantages and the disadvantages of each one in order to plan in short, medium, and long term, obviously, and with the main focus of, I think, two things: cover the demand or the demand predictions that for the next 10 years, they obviously are not going down. And the second one is ensuring grid resilience. And human society now is so reliant on energy that we can not even assume a blackout anymore. I mean, if we spend 3 hours with no energy, that is complete madness. In Spain, my parents just went, I don't know, 3-4 hours without energy, without power, maybe more, and they were mad about it. We need to ensure that no blackouts occur, and that's with a mix of all of the existing technologies and the ones that are to come, obviously.
Yeah. Well, I hope that you're right about that. And the only thing I would say about the Spanish blackout is if we had to have one in the springtime during the daylight hours would be good.
Yeah.
But hopefully we will not. And with that, thank you all. Diego, Dan, Derek, and Alex. That'll conclude our panel. We're going to have some great stuff this afternoon on cybersecurity and transmission, and a tremendous keynote is coming up. So with that, Matthew, do you want to take it away?
I'll take it away just to say it's time for my favorite part of every workshop agenda, lunch. It is served just around the corner in our kitchen. We'll be back at 12:40.
Oh, since that morning.